Hello everyone, today we're going to talk about an interesting topic called the SN2 reaction, which is everyone's favorite reaction. After this lecture, you should be able to distinguish SN2 reactions from a bunch of different reactions, and you should also be able to identify the substrates which are suitable for SN2 reactions and be able to write the mechanism for SN2 reactions. Before we get into the details of SN2 reaction, let's get ourselves acquainted with some of the terminologies which will help us to understand the SN2 reaction better. The first one that we have here is nucleophile. What is a nucleophile? It is an electron-rich species which wants to go and attack a nucleus, or simply an atom which is electron deficient. So the term phile means loving, so basically it is nucleus loving. And the next one is the electrophile. Electrophile is an electron deficient species which wants to be attacked by a nucleophile. It is normally represented as E+, whereas the nucleophile is represented either by Nu or Nu- depending on the charge on it. And then finally, the leaving group. The leaving group could be an atom or group of atoms which departs from the molecule, leaving the rest of the molecule behind in a reaction. Okay, so with that, let's talk a little bit about the nucleophilic substitution reaction in general. What is a nucleophilic substitution reaction? In a nucleophilic substitution reaction, a nucleophile goes and takes the place of a leaving group. Here is an excellent example for a simple nucleophilic substitution reaction where methyl bromide reacts with hydroxide ion to give methanol and bromide ion. Let's identify the different species in here. So our hydroxide ion is going to be our nucleophile. And here we have our substrate, which is an alkyl halide. Alkyl halides are excellent substrates for nucleophilic substitution reaction. When you consider an alkyl halide, this bond right here, the CBr bond, is going to be polar. And that's because of the electronegative bromine add, which is going to continuously withdraw the electrons. And therefore, this is going to be partially negative. And this carbon is going to be electron deficient, and therefore it's going to be partially positive. And the dipole moment is going to be in this direction. And because of this electron deficient carbon, the nucleophile can actually go and attack this carbon. And here we have our leaving group. Okay, a nucleophilic substitution reaction can be of two different types, SN1 and SN2. Now, for this lecture, we are primarily concerned about the SN2 reaction, and let's talk about what is an SN2 reaction. Let's break it down. S stands for substitution, and N stands for nucleophilic, and 2 stands for bimolecular. So all put together, it's called as bimolecular nucleophilic substitution reaction. When you say bimolecular, there are going to be 2 species which are involved in the rate determining step. Okay, now let's go on to the mechanism. In order to propose a mechanism for any reaction, you need to study the kinetics of the reaction. So 2 people, Hughes and Ingold, they were able to predict the mechanism for this reaction, for this SN2 reaction, to be a concerted reaction where there is only one single step with no intermediates. And the mechanism is going to be super, super simple, where you can see that this hydroxide ion will go and attack this carbon in a site that's exactly opposite to that of the leaving group, and the leaving group is going to leave. And both of these steps happens in the same time. And remember, I'm going to tell this mechanism one more time. The hydroxide ion, which is our nucleophile, will go and attack this carbon from the side that's exactly opposite to that of the leaving group, and the leaving group is going to pack its electrons and leave. So and this is called as the backside attack. Now, why should the nucleophile come and attack from the backside and not from the front portion? So very simple answer that you can give is because the leaving group is actually occupying the front portion, the nucleophile cannot come and attack from the front side, right? But there are also other reasons. One main reason is that when you consider the orientation of the orbitals around this electrophile, it is only going to let the nucleophile to come and attack from the backside. And also remember, this bromine right here is an electronegative atom, and it is going to have a bunch of electrons around it. And the nucleophile, which is also going to have electrons around it, will definitely be repelled by the leaving group. And therefore, it's not going to let it go and attack in the front side. Okay. And these two people, when they did the kinetic study, they got three important evidences. Now let's look into the very first evidence. The rate was directly proportional to the alkyl halide and as well as the nucleophile. When you consider this reaction is going to have a transition state, which is going to look more like this, where you can see that this bond right here, this carbon right here, is going to have three bonds which are completely formed and two bonds which are partially formed. While this bond is forming, this bond right here is breaking. And this transition state is the one which is responsible for determining the rate of the reaction. And within this transition state, you can see that there is a nucleophile and there is also the alkyl halide. So which means as you increase the concentration of the alkyl halide or the nucleophile, the rate of the SN2 reaction is going to increase. Or in other words, if you're going to decrease one of these, the rate is going to decrease because there is going to be decreased collision between the two reactants. The second piece of evidence they were able to get was the inversion of configuration. Now, when you're going to take a chiral alkyl halide, there is going to be an inversion in configuration. Now, why should an inversion take place? Now, remember, the nucleophile is going to come and attack from the backside. As the nucleophile approaches this carbon right here, this carbon is going to have three CH bonds or three hydrogens, and you have the leaving group. As the nucleophile approaches this carbon right here, all these CH bonds are going to try to move away from the nucleophile and its attacking electrons. And in the transition state, the CH bonds are going to be all planar. They're all going to lie in the same plane. And the carbon is going to be pentacoordinate, which means it's going to have three bonds. And there are two partially formed bonds, and it cannot stay there for a long time. One of the bonds need to break, and obviously it is going to be this bond. And until the nucleophile establishes the bond with the carbon, the CH bonds will keep moving on the opposite side, trying to look more like a flipped umbrella. Okay. While there may not be any stereochemical implications in this compound right here, which doesn't have any chiral center, for a compound like this, where there is a chiral center, there is going to be an inversion in configuration. So if it's going to be R, then it's going to get changed into S. Okay, so this inversion in configuration is called as Walden inversion, named after Paul Walden, the scientist. And the last piece of evidence that they were able to get was the relative rates of the alkyl halides was found to be of this order, where you can see that the methyl halide reacts faster in an SN2 reaction, whereas the tertiary alkyl halide reacts much slower in this reaction. Now, why it should happen? Remember, it's exactly again for the same reason. You have your nucleophile, which comes in a direction that's opposite to that of the leaving group, and it needs to go and find this electron deficient carbon. Well, in the case of methyl halide, it's going to be super easy. Whereas in the case of tertiary alkyl halide, the nucleophile will try hard to get to this electron deficient carbon. Remember, there are three alkyl groups which are blocking its way. And it's super, super hard for the nucleophile to find this electrophilic carbon that this SN2 reaction of the tertiary alkyl halide does not even happen. Okay, apart from the alkyl halide itself, there are also other factors which is going to determine the rate of the reaction, such as leaving group, nucleophile, and as well as solvent, which we'll be covering in the next class. Okay, applications of SN2 reaction. There is an important SN2 reaction that happens in living organisms where noradrenaline is converted into adrenaline. So here you can see there is this nucleophile which goes and attacks SAM, which is S-adenosyl methionine, and this is going to be our entire leaving group. The sulfur right here is activated to get it converted into a good leaving group. Okay, this is one of the important biologically relevant SN2 reaction. So on the whole, SN2 reaction is a bimolecular nucleophilic substitution reaction, which happens in one single step, and the rate is found to be proportional to the alkyl halide and the nucleophile, and there exists a inversion in configuration, and the relative rates is going to be proportional, is going to be based on the steric hindrance of the alkyl halides. I have two problems for you guys to work at home. Finish that and then bring it to the class next week. Thank you.